If you recall, last time we were integrating some rational functions. A rational function just has a polynomial over another polynomial. And the key to integrating rational functions, or one of the keys to integrating rational functions, is that the integral of 1 over x squared plus 1 dx. Oh, let's do our modified one, where instead of just plus 1, because we graduated after, we graduated the x squared plus 1 business. So let's go 1 over x squared plus a squared dx is 1 over a arctangent x over a plus c. The other one we needed was the integral of x over x squared plus a squared dx is 1/2 natural log of x squared plus a squared plus c. Here's all we need for the irreducible quadratic denominators. That is quadratic denominators with complex zeros. This is all we needed to deal with quadratic denominators with complex zeros. I have x squared on top. That's not what we needed. If I could stop writing the wrong thing, that would be great. Good thing that that got recorded. So if we have a quadratic denominator with complex zeros, all we need to know about is what happens if it's degree 0 on top or degree 1 on top. We don't have to worry about degrees greater than 2. If the degree of the numerator is greater than or equal to that of the denominator, we use long division to rewrite the polynomial. So algebraic answers to anything that's not this. If the degree of the numerator is greater than or equal to the degree of the denominator, then use long division. That's why we only need these two when we have a quadratic denominator with complex zeros. We also saw that if there was an x term in the quadratic denominator with complex zeros, then we complete the square. That is, rewrite x squared plus bx plus c into x minus h squared plus k. And then we can substitute. Now, this is when we have a quadratic denominator with complex zeros. The other part we need is what happens if we have a linear denominator, if it's just like a 1 over x. So what happens if we have a denominator that's not quadratic, but linear, or a power of a linear denominator? So, for example, if I wanted to integrate, say, 1 over x minus 3 dx, the nice thing is, the reason I save this one for after the quadratic business is that it's pretty simple. We're just going to do a substitution. W can be x minus 3. Then the function that we're plugging into is 1 over w. And in a nice linear substitution like this, the dw is equal to dx. So if w is x minus 3, then dw is just 1 dx. So this integral we're integrating the function 1 over w dw. The integral of 1 over w is natural log of w. Oh, excuse me, natural log of absolute value of w plus c. And w is equal to x minus 3. So we get the natural log of the absolute value of x minus 3 plus c. If we have a coefficient on the x, then that's going to be part of the dw, and it'll just get divided out. So if there's a coefficient on the x, for example, 1 over 5x minus 3 dx, our substitution is still going to be the denominator. So w is 5x minus 3. The function that we're going to be integrating is still 1 over w. And dw, here's where things are different, is going to be 5 dx. So that means that 1/5 dw is equal to dx. So instead of just integrating 1 over w dw, we'll integrate 1/5 times 1 over w dw. So we will be integrating on 1/5 from the dw, the integral of 1 over w dw. So we'll just have a 1/5 natural log of absolute value of w plus c. And so we'll have 1/5 natural log of absolute value of 5x minus 3 plus c. We also need to concern ourselves with the same things that we had before. Here I had a constant over the x minus 3, a constant over a linear. What if I had an x over a linear? That refers to the first thing that we pointed out up here. If the degree of the numerator is greater than or equal to the degree of the denominator, then use long division. So if we have to integrate something with an x on top, so if, for example, I'm going to run out of space, all the other rules still apply that aren't quadratic specific, like with completing the square. So if, for example, I have, let's say, 2x over 5x, let's not use 2x. Let's do 2x over x minus 3 dx. What we notice in this rational function is that the degree of the numerator is equal to that of the denominator. And so that should trigger us to do long division. The degree of the numerator is 1. The degree of the numerator is 1, and the degree of the denominator is also 1. So that triggers long division. So I'm going to divide x minus 3 into 2x. And we ask ourselves, how many times can we subtract x from 2x? And we can do that 2 times. 2 times x is 2x. 2 times x minus 3 is minus 6. And then we will subtract. How many times can we subtract x minus 3 from 2x without going negative? We can do that 2 times. The 2x's cancel out. That's the plan. That's what's supposed to happen. And then we have 0 minus a negative 6, which is plus 6. So we rewrite our integral as the integral of 2 plus 6 over x minus 3 dx. That first term is the polynomial, and the second term now has a degree of, the degree of the numerator is now 0, and the degree of the denominator is 1. So long division has worked. The integral of 2 with respect to x is 2x. The integral of 6 over x minus 3 is 6 times the natural log of the absolute value of x minus 3 plus c. When we talk about completing the square, we're specifically referring to quadratics. So that's not going to apply with these linear denominators or powers of linear denominators. We should note that when we have degree 1 over degree 1, then we get a constant plus degree 0 plus degree 0 over the degree 1. If I increase this exponent to, let's say, an x squared, then I'll have a linear term, a constant term, and then the fraction. All right. Let's talk about powers of linear. If, for example, I didn't just have 1 over x minus 3, I had 1 over x minus 3 to the 5th power, the x. We're going to do the same thing. We're just going to end up with, we're going to do the same substitution that we did with this natural log business. But now, instead of being an exponent of -1 and coming up with natural log when we integrate, we're going to be integrating it with an exponent of -5, and then just be able to do add 1 to the exponent, divide by the new exponent. So our w is going to be x minus 3, just like it was before. The function that we're plugging into is changed, though. Y is now 1 over w to the 5th power. Our dw is still just going to be a 1 times dx. So our integral is going to be 1 over w to the 5th dw which we'll read as w to the -5. So this will read as w to the -5. So to integrate, we add 1 to the exponents and divide by the new exponents. -5 plus 1 is -4. and we divide by the -4. So we get -1/4 x minus 3 to the -4 plus c. So if we get powers of linear functions or powers of linear polynomials, we do the same thing. If the denominator is linear but not monic, that is, the leading coefficient is not 1, then a similar thing happens to our natural log. That happened in our natural logs. Let's suppose that we had the integral of 1 over 2x minus 3 to the 5th power. What's going to change is that our dw is not just going to directly replace the dx, because our w is 2x minus 3 this time. The function that holds the dw is still a 1 over w to the 5th. So we're still just integrating 1 over w to the 5th, but now the dw is going to introduce an extra factor. So the dw is 2 times dx, and so a 1/2 dw is equal to the dx. So the dx is now getting replaced with 1/2 dw, not just dw. So that's just going to pull a 1/2 out in front of our integral. We're still integrating 1 over w to the 5th. dw. So there's the dx getting replaced with a 1/5 dw. The rest of the integration works the same. The integral of 1 over w to the 5th, we're still going to read that as a w to the -5. So when we integrate that, we'll still have -1/4 w to the -4 plus c, but then this will all be multiplied by 1/5. So we end up with -1/20 2x minus 3 to the -4 plus c. I put 1/5 and I meant to put 1/2. Sometimes a 2 looks like a 5. It's useful to think about, just from a process standpoint, it's useful to think about, take the derivative of our answer, to think about where all these extra factors come from. Because a lot of times we start doing things and we just try to do these things by rote, just kind of automatically do them. But it's useful to take a step back and say, well, where do all these things come from? So the derivative of -1/8 times 2x minus 3 to the -4 is, we'll take the -1/8, we multiply by a -4, multiply by the exponents, reduce the exponent by 1, and then multiply by the derivative of the inside. So the 1/4 came from the integral process, and the 1/2 came from the derivative of the inside. And so this gets us back to 2x minus 3 to the negative 5, which is what we started with. Always good to take the derivative of your integrals to see if they go back to the original. That's why if you have a math book, you should never bother putting the answers to the odd numbered problems when the question is solving the equation. Because if you want to know if your solution to the equation is correct, all you have to do is plug it into the equation and check. Now, we save time by being able to look it up in the back of the book. But speed is not the issue. Really, if you want to save time, just have someone on hand to do your math for you. I saved a lot of time when I was renovating my house by having someone else do it for me, the parts that I didn't know how to do, so I wouldn't have to take the time to learn it, because at that point, time was the issue. But we're not here to build a house that we have to live in. We are here to learn stuff, so it's important to take the time to understand how it all goes together. Does that make sense? All right. So we've talked about rational functions where the denominator is linear or a power of a linear factor, or where the denominator is a quadratic with complex zeros. What if our denominator is, say, quadratic or even higher degree with real zeros? What if our denominator is quadratic with real zeros? That is, it's factorable over the real numbers. I closed the window that I needed. So for example, what if we wanted to integrate? What if our denominator was x squared plus 4x minus 5? And let's put this under a 5x plus 13 for reasons. So here we're integrating a rational function. The denominator is quadratic, but it has real zeros. This denominator is factorable. So the denominator is quadratic, but it has real zeros. This denominator is factorable. I can write this as x minus 1 times x plus 5. The first thing we should notice is that the degree of the numerator is less than the degree of the denominator, so long division is not necessary. So that's an important thing to note first. That's why I skipped that first check. But now we look at the denominator and we see that the denominator is quadratic, but also factorable. So what we're going to do is take this and reduce it into two integrals with linear denominators. We're going to do a process. We're going to rewrite this rational function as the sum of two rational functions. One of them will have a denominator of x minus 1, and the other fraction will have a denominator of x plus 5. Since the numerator had a degree that was less than the denominator, we know that in this sum, the degree of the numerator will still be less than that of the denominator, which in this case means they'll be constants. So what we're going to do is a process called partial fraction decomposition. This one actually works out to 3 over x minus 1 plus 2 over x plus 5. And the process that takes us from this rational function to this rational function is called partial fraction decomposition. You can see that if we rewrite this fraction, 5x plus 13 over x squared plus 4x minus 5, if I can rewrite it as 3 over x minus 1 plus 2 over x plus 5, then it's really easy to integrate based on what we just learned about integrating rational functions with linear denominators. The integral of 3 over x minus 1 will just be 3 times the natural log of the absolute value of x minus 1. The integral of 2 over x plus 5 will just be 2 natural logs of absolute value of x plus 5 plus c. So partial fraction decomposition is a technique wherein we rewrite a rational function as a sum of rational functions where the denominators are factors of our original fraction. We decompose the fraction into a sum. So what we're doing is we're writing the fraction as a sum.
Wait, Professor, how did you get the 3 and the 2 on the denominators?
That's I used partial fraction decomposition, and I have secret math knowledge. So this is what we need to talk about next. I didn't tell you how I did that. I used magic. Secretly, what I did was I said, I want it to look like 3 over x minus 1 plus 2 over x plus 5, and then I added those together. I added these together to get 5x plus 13. And then I pretended that I could decompose this really fast. So the last thing that we need to talk about in this rational function, integrating rational function business, is how to do partial fraction decomposition. And that's what's up next. How to partial fraction decomposition. It really comes down to knowing what you want to happen and then making that happen. Knowing what you want to happen and then making that happen. So you start off with looking at 5x plus 13 over x squared plus 4x minus 5, recognizing that the factors down here are x minus 1 times x plus 5, and knowing that this will make two fractions, an x minus 1 and an x plus 5. Since the degree of the numerator started off less than the degree of the denominator, in each term, the degree of the numerator will be less than the degree of the denominator. Right now, you're taking my word for it, but that means that the numerators will be constants. So we just if we know that we're going to have fractions with denominators of x minus 1 and x plus 5, we want those numerators to be constants. Then we just add these two with the a and the b. This is going to be a times x plus 5 plus b times x minus 1 over x minus 1 times x plus 5. Then if we multiply all this out, I've got ax plus 5a plus bx minus b. So I have an x coefficient. If I add my like terms, I have a plus b times x, and my constant is 5a minus b. This is supposed to equal 5x plus 13. So if these two fractions are equal, that tells me that a plus b must equal 5. And also that 5a minus b is equal to 13. This is a system of equations that we can solve for a and b. In particular, if I add these two equations together, I get 6a, 0b equals 18, and that tells me that a is equal to 3. And if a is equal to 3, 3 plus b is equal to 5, so b is equal to 2. And we have decomposed our fraction partially. I don't know if that's how the wording is supposed to go. We've done partial fraction decomposition. And now we can integrate. Now, things are getting a little bit weird algebraically, so the natural question is going to be, why don't we just use a computer to do partial fraction decomposition for us? Because if we're going to use a computer to do the partial fraction decomposition, we should just use that same computer to do the integration for us. So, oops, I have the wrong one in. If I input into, say, Wolfram alpha 5x minus 13 divided by x squared minus, oops, plus 4x minus 5. One of the things that I'm going to get is not only the decomposition of this. Is it going to give me the decomposition? Oh, it's not. How funny. Yeah, sometimes Wolfram alpha is a jerk. But one of the things that it's going to give us is, I put minus 13 plus 13. I wonder it was not working. There we go. One of the things that it gives us is our partial fraction expansion, but we don't want to use that to integrate, because if we just scroll down a little bit more, one of the things that's going to be there is the indefinite integral, which is 3 log 1 minus x plus 2 log x plus 5. So no surprises here. But that's not the point. Coming up with the answer quickly is not the point. Understanding how rational functions are put together, that's the point. We're trying to understand fractions in a different base. Any questions? All right, that's going to do it for today. Tomorrow we'll talk a little bit more about partial fraction decomposition, and then we will have had a nice complete discussion about integrating rational functions. And then you'll wonder, when am I ever going to do integrating rational functions ever again in my life? And I'll be like, oh, next semester in Calc 2. And then you'll be like, oh, yeah, but after that, I'm like, oh, never. And so you'd be like, oh, do I have to know this? And the answer I've discovered is always no. You don't. Everything will be fine if you don't know this. Someone else might find it useful, but you can decide, even though it's rather premature, that this will never be useful to you, and that's okay too. Any questions? Comments? All right, that's going to do it for today. I will see y'all on tomorrow. Hopefully, Canvas will get its stuff together. Actually, hopefully, Jeff Bezos will get his stuff together, stop flying to friggin' space, and give us some web services that work. I mean, the outage has been going on for at least 3 hours, which I think is just too long for the amount of money that Amazon Web Services pulls in. I mean, we collectively are paying a whole lot of money for this, so I think it's okay that we demand service. Like if I live in a town where there is exactly one person who is a mechanic, I'm going to be okay with it taking a little bit longer time to get my car worked on. Because it's like one guy fixing cars. Especially if I live out in the middle of nowhere, it's going to take me a long time to get the parts that we need. So we'll just kind of have to deal with that. But when collectively we're paying Amazon Web Services like huge, gigantic piles of money, you better be ready to fix stuff when it goes down. Because in December, the week before finals, to have Canvas problems, that's a disaster. And we are not getting the service that we paid for. So stop flying to space, you greedy bastard, and get stuff working. You know what I mean? I know he's not literally in charge, but he reaps all the benefits. So, and he's the public face of the company. So welcome to the fire line, Jeff. You know what I mean? He can take it. I'm sure he's got plenty of ego. All right, that's going to do it for today. I'll see y'all on tomorrow. Hopefully, I will get some problems going for you. But that's, I guess that's up to Canvas now, isn't it? So Canvas, get your shit together. That's it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.